Until now, we saw a component that simply opposes current. Now let's study a component that stores energy and opposes changes in current. That is the inductor. An inductor is a passive two-terminal electrical element that stores energy in its magnetic field when electric current flows through it and opposes any change in current. Imagine a coil of wire. When current flows through the coil, it creates a magnetic field around it. This magnetic field stores energy. What happens if we try to change the current? Suppose current is flowing through the inductor. The magnetic field already exists. Now imagine trying to suddenly increase or decrease the current. To do that, the magnetic field must also suddenly increase or decrease. But changing a stored magnetic field instantly is extremely difficult. The inductor opposes this sudden change. Because the magnetic field cannot change instantly, the current cannot change instantly either. So at the exact switching instant, current at 0 minus is equal to current at 0 plus. This means just before switching, if current is 5 ampere, just after switching, current is still 5 ampere. The current may start changing afterwards, but not at the exact switching instant. How does inductor prevent sudden current change? An inductor creates voltage whenever current tries to change by this formula. This voltage acts in a direction that resists the change in current. Think of it like more force trying to change current, more opposing voltage produced by the inductor. What if we demand instantaneous current change? Suppose we want current to jump from 0 to 10 ampere instantly. That means huge current change and zero time available. So di by dt, that is rate of change of current, is infinity. Using the voltage equation, we have V equal to L into di by dt, which is nothing but infinity. The required voltage becomes infinitely large, but an infinite voltage cannot exist in a real circuit. Therefore, instantaneous current change is impossible. At the switching instant, current is known. That is, the current must equal its previous value. So I0 minus equal to I0 plus. Voltage is not fixed. The inductor can develop whatever voltage is necessary to maintain current continuity in the ideal mathematical model. This is why gate questions often ask, find current immediately after switching. The answer usually comes from the current before switching. What happens after a long time? Now suppose a DC source is connected for a very long time. Eventually current stops changing. The current becomes constant. The graph becomes a flat line. If current is constant, a constant current means di by dt is 0. Substituting into V equal to L into di by dt, we get V equal to 0. So the inductor has 0 voltage across it. Magnetic flux is the total magnetic field passing through a given surface, and flux linkage is the total flux linked by all turns of a coil. Phi, which is magnetic flux, is given as P into A into cos theta, where B is flux density, A is area, lambda is nothing but your flux linkage, N is the turn count. Inductance is the property of a circuit or element that opposes change in current by inducing an electromotive force due to changing magnetic flux. So we have the formula L equal to d lambda by di, where L is the inductance, I is the excitation current. One thing to know here is, for linear inductors, this simplifies to L equal to lambda by I. The voltage across an inductor is proportional to the rate of change of current through it. That is, V equal to L into di by dt. Faraday's law states that a changing magnetic flux induces an electromotive force in a circuit proportional to the rate of change of flux linkage. That is, E equal to minus d lambda by dt. For linear inductors, this simplifies to E equal to minus L into di by dt. Terminal voltage V is given as L into di by dt. The negative sign in Faraday's law explicitly arises from Lenz law to show opposition to the change causing it. However, under the standard passive sign convention used in circuit theory, the terminal voltage is written as V equal to L into di by dt. Energy stored in an inductor is the energy stored in its magnetic field due to the current flowing through it. It's given as half Li square, where W is the stored energy in joules. Unlike a resistor, an ideal inductor does not inherently dissipate energy. It borrows power to build its magnetic field, then returns it completely when the field collapses. The inductive reactance is the opposition offered by an inductor to alternating current due to its inductance. Scalar reactance XL is given by omega L, which is 2 pi f L. Complex impedance ZL is given as JXL, which is nothing but J omega L. Here XL is inductive reactance, ZL is inductive impedance, omega is angular frequency, J is imaginary operator, which is root of -1. Reactance magnitude increases linearly with frequency and the phase shift is exactly plus 90 degree. At infinite frequency, that is when omega tends towards infinity, its impedance mathematically approaches infinity in the ideal model, causing an ideal inductor to act as an open circuit. RL transient response. The transient response of an RL circuit describes the variation of current with time when a DC voltage is suddenly applied or removed. Here, the time constant tau is given as L by R. I of t is nothing but V by R into 1 minus e to the power minus t by tau. Assume 0 initial inductor current, that is I0 minus equal to 0, and a DC step input at t equal to 0 in a series RL circuit. Current rises gradually due to magnetic opposition. For an ideal first order RL system, the response reaches approximately 63.2% of its final value, that is V by R, at t equal to tau, hitting steady state after roughly 5 into tau. Mutual inductance. When two coils are placed close together, the magnetic field produced by one coil links with the other coil. This magnetic coupling between coils is called mutual inductance, which is given by this particular formula. Here, K is nothing but coefficient of coupling and its value lies between 0 and 1. If all magnetic flux of one coil links with the other coil, we call it as perfect or tight coupling. In that case, K equal to 1. And M or mutual inductance is given by this particular formula. The dot on a coil shows the reference point of current and magnetic flux. Imagine current entering the dotted terminal. If current enters the dotted terminal of both the coils, the magnetic fields are in the same direction, hence causing the aiding. And this leads to the flux getting added up. While if the current enters the dotted terminal of one coil and the undotted terminal of the other coil, the magnetic fields are in opposite directions and flux cancels. In case of series connection, for n number of uncoupled inductors, that is mutual inductance being 0, we have L equivalent given by this equation. But if we are considering two coupled inductors where M is not equal to 0. First case is of series aiding, that is current produces magnetic fields in the same direction and fields help each other. So in this case, this is our formula. While if it is series opposing, that is magnetic fields oppose each other, in that case, this is our final equation. In case of parallel connection, for n uncoupled inductors where M is actually 0, 1 by L equivalent is given by this equation. For two coupled inductors where M is not equal to 0, parallel aiding, that is dots connected together, provides this particular formula, while parallel opposing, we have this particular formula.